Hello everyone, welcome to Basic Chemistry Plus. Today we are going to discuss about the intermolecular forces. This is the major part of the states of matter chapter. Because without this portion, you would not be able to understand the topics in the states of matter like the Maxwell distribution curve or the Amagas curve and all those things. They are all related to intermolecular forces. So definitely we need to understand this thing first. Only then we would be able to grasp up all the topics those are going to be taught in the end. Now, today we are going to talk about the intermolecular forces only, and we are going to look into it in a more vivid manner. Whatever is written in our book, there are some subtle, detailed discussions can be done in this topic. And this is what we are going to do today. So first, what is an intermolecular force? So as you can see over here, the intermolecular forces are not like the bondings. When you learned about the bondings, you have learned that they are mainly the interatomic forces, isn't it? Interatomic forces. Because the bondings are done in between the atoms. You have learned about ionic bonding, you have learned about covalent bonding, coordinate covalent bonding. In each and everywhere, you have seen that the bonding is happening between two atoms. But here, we are not going to talk about this. Here, we are going to talk about the forces which is working in between two molecules. So, let's say I have a water molecules and another water molecule. In between these two water molecules, the force which is there, that's called the intermolecular force. Now, you have heard about this earlier as well. Do you remember in class 9, you have heard about this topic, intermolecular forces. This is the force. Like, you have heard this in this way. Let's say I have a solid, I have some liquid. So, in the solid, the particles are very closely aligned to each other, isn't it? Because they have high intermolecular forces. In case of the liquids, the particles are a bit far away from each other because they have low intermolecular forces and they have spaces in between the particles of liquids. So this is what we have learned. We had a preliminary idea about the intermolecular forces. Today we are going to learn about this in a bit more detailed manner. So first, we are going to learn how many types of intermolecular forces are there actually. So there are mainly two types of intermolecular forces. One of them is van der Waals force of attraction. Van der Waals force. Okay, by the way, it can be attraction, it can be repulsion, both of them, right? And the other one is hydrogen bonding. This is another intermolecular force which is working in between the molecules, right? Now, definitely this is not the end. In apart from these two van der Waals and the hydrogen bonding as well, we see ion dipole interaction as well. So that is something we are going to talk as well in this video. Now, first we are going to learn about the van der Waals forces. So, van der Waals forces. There are mainly three types of van der Waals forces. First is London. Second, Kissom. And the third one is Dubai. These are the three types of van der Waals forces. Those are there. Landon force over here, this is also known as induced dipole interaction. So we call it induced dipole interaction. Or sometimes instead of induced dipole, they also call it instantaneous dipole induced dipole interaction. Okay. And the Keystone force over here that you can see, this is nothing but dipole-dipole interaction. So when two dipoles are there, we see the Keystone force. And the Debye force, it's also known as dipole-induced dipole interaction. Okay. So now let's talk about them one by one. So let's start with the Landon force. Guys, I think you know about the states of matter, and we have heard about it that there are majorly three fundamental states of matter, right? Fundamental. So definitely you know that. Like nowadays there are so many YouTube videos about it. Like there are 15 states of matter. So like considering all of them, but all I'm talking about right now is the fundamental ones. So there are three states of matter. Definitely you know that: solid, liquid, and the gases. But my point is, the states of matter, if you just talk about it, you can either see the solid state, or you can see the liquid state, or you can see the gaseous state of it there, right? And sometimes when solid convert into a liquid, when it is on its melting point, at that time there is a solid liquid equilibrium that we can see, right, at the melting point. When it is taking the latent heat in, at that moment we have solid as well as liquid, both the states of matter together at that time, right? Now sometimes we can also find these three states of matter together at one temperature and a pressure. What I mean to say is, there is a particular temperature and pressure for each and every molecule where we can find the all three fundamental states of matter together. We call that particular point is known as triple point. That particular point is known as triple point. Triple point is a point where all the three states of matter are present. So if I just give you an example, at 0.01 degree centigrade and 4.58 mmHg mercury pressure, water remains in all these three states: solid, liquid, and gas. So the triple point for water is 0.01 degree centigrade. Now, the Landon force over here that we are talking about, this force is mainly seen in non-polar molecules. We can see them in the non-polar molecules. So let's say I have any sort of noble gases. There we can definitely see the Landon force of attraction. So guys, let's talk about the Landon force a bit more in a bit more detailed manner. So I guess you know that the noble gases can also be liquefied, isn't it? Like if I take argon for an example, for that you need to take it to 186 degree centigrade to liquefy it. So it's pretty low. It's a pretty low temperature, but yeah, we can still liquefy them. Now to liquefy them, or to condense the noble gases, we need this force of attraction. This Landon force of attraction is the reason behind all this condensation in the noble gases. So what is this Landon force of attraction interaction over here? If we just look into it, let's say I have a particular molecule right now. Let's say this is argon for us. And we know that argon is a non-polar molecule, isn't it? This is a completely non-polar molecule. You can never make it polar. But there is a nucleus in it, and there are the electrons completely roaming around it, right? But all the electrons, this is a symmetrical system. This diagram is a symmetrical diagram, isn't it? It's a symmetrical diagram. But you know that all the electrons are moving. They're not static, they're dynamic. So they're moving from one place to another place. So as a result, there can be a particular instant where, or a particular fraction of second, where this electronic arrangement for a very few seconds, it can rearrange itself in such a way that one side of it gets more amount of electron than the other side. As the electrons are moving, as they are dynamic, because of that, if sometimes there is an asymmetry getting generated, then it becomes instantaneous dipole. Why do we call it dipole? Because in one side we have more electron, in the other side we have less electron. So can we say that the one of the sides are delta negative and the other one is delta positive? Try to understand what I'm trying to say over here. What do we mean by these deltas? Deltas are these Greek letters which is going to tell you about the difference. Now this delta negative is not exact negative. This delta negative is nothing but a partial charge. It's a partial distribution, right? So for an instance, if this happens, then what would happen? There's a desymmetry or asymmetry getting generated over here, and because of this asymmetry, there is a generation of a instantaneous dipole. Instantaneous dipole. There's a generation of instantaneous dipole. Now, when we talk about two argon molecules, those who are just beside each other, when we talk about two argon molecules just beside each other, and one is having this instantaneous dipole generated. So why is that instantaneous dipole getting generated? Because the electrons are moving, and sometimes they're symmetrically arranged, but sometimes it may happen that the electrons, because of their movement, they are not equally arranged. So in one place, for one instance, the density of electron is more than the other side. If that happens, then that is called an asymmetry, which is getting generated for an instant. That's why we call it instantaneous dipole. So if that instantaneous dipole generates in one of the molecules, one of the argon molecules, then what would happen? Then because of this, the other argon molecule, which was completely nonpolar, that would get induced. And as a result, this side is positive. So in the other argon, the electrons would arrange themselves in this way because of this induction, because this positive would attract this negative and there would be an induction happening. So this is an instantaneous dipole and this is an induced dipole. That's why we call it an instantaneous dipole induced dipole interaction, which is known as Landon force. This Landon force that we are talking about, this was discovered by Fritz Landon. He told us that this force is proportional to 1 by r to the power 6, where this r, one more thing, up to 500 picometer. After that, this Landon force won't work. Now what is this r? This r is the distance between two nonpolar atoms. So, or molecules, whatever you say it. Because argon, for them, the atoms and the molecules would be having the same symbols, right? So, this r is the intermolecular distance. Molecular distance. Okay. Now, definitely you can see that this instantaneous dipole induced dipole is completely dependent on the polarizability of a molecule. polarizability of a molecule. Because anyway, this is nothing but the polarization, isn't it? When we are deforming the electron cloud, that is called polarization, and this is completely dependent on the polarizability of a molecule. So we are definitely willing to know now what are the parameters in which this instantaneous dipole induced dipole interaction, means the Landon dispersion force, is dependent on. So the first thing is the size of the molecule. The first thing is the size of the molecule. It's definitely dependent on the size of the molecule. So let's say, for an example, I have CH4, I have SiH4, and I have GeH4. So guys, definitely the CH4 is having the boiling point values as 112 Kelvin, 161 Kelvin, and 183 Kelvin. These are the values for boiling point. Okay, that's the boiling point value. Now, if you look into it, CH4 is having the least boiling point and GH4 is having the most boiling point. Definitely that is understandable, because I told you this depends on the size of the molecule. So definitely the size of the hydrogen is not changing, but definitely the size of the germanium, silicon, and carbon, these atoms are changing. And germanium is having the highest size. So that's why we can say that this should be having the highest boiling point. I guess understood that. Now, the second factor, number of electrons. So this Landon dispersion force also depends on the number of electrons present in that molecule. So let's say I am talking about a noble gas which is helium, and let's say I'm talking about another noble gas which is radium. So you know that the radium is having much more electrons than helium. So more electrons. So if it is having more electrons, now if we just try to find out their boiling point values, so definitely radium has more boiling point, just because it is having more electrons in it, right? Now, the last parameter in which it depends on is the molecular structure. So in molecular structure as well, the Landon force is dependent. So as you can see over here, let's say I have, let's say, make an N pentane, 1, 2, 3, 4, and 5. This is N pentane. And let's say I have, what should I take? Neopentane or isopentane. So CH3, CH. So this is isopentane. Okay. Now if we just try to compare between them, who would be having higher boiling point? Now definitely you can. So in between N-pentane, isopentane, who would be having higher boiling point? That's the question. Now the answer is going to be N-pentane, because you can see the molecular structure is also a very important point over here. And now why it is N-pentane? Because in N-pentane the surface area is more. The surface area is more in N-pentane. Now you might be thinking, why the boiling point is dependent on the Landon forces? So it is fairly understandable if you just think about it. What are we trying to do when we are trying to convert a liquid into a gas? What are we trying to do over here? So in the liquid, the molecules are very close to each other. But when you talk about the gases, the molecules are far away from each other. So definitely we are trying to break the intermolecular forces when we are trying to heat somebody. When we are trying to change the states of the matter, we are trying to break or make the intermolecular forces. Here in boiling point, we are definitely trying to break the intermolecular forces. That's why if you have more intermolecular forces, if you have the intermolecular force, if that's strong, so the boiling point would be high. Now you can see that's what we are talking about. So the intermolecular forces depends on the size of the molecule. So for GH4, the intermolecular force is strong. That's why its boiling point is higher. For radium, the intermolecular force is strong because it has more electron. That's why its boiling point is also higher. And for when you talk about the molecular structure, N-pentane is having the highest boiling point among N-pentane, isopentane, and neopentane, just because it has higher surface area. Higher surface area means higher Landon force. So higher intermolecular force. High intermolecular force is proportional to the boiling point. So definitely that's the relation. So this is what we have learned about the Landon force. Now we are going to talk about the Kissom and the Debye force. Both of these forces are not that much difficult to understand. If you look into Kissom force is also known as dipole-dipole interaction. Dipole-dipole interaction. So definitely you can see that we need permanent dipoles over here. So we need molecules, those who have permanent dipoles with permanent dipole. That's called the Kissom force. Now, let's say, what are the examples for that? Let's say I have HCl. I have an HCl molecule. So HCl has a permanent dipole. If you just look into it, if I talk about HCl molecule, Cl, the electronegativity of Cl is more than the electronegativity of hydrogen, definitely. That's why what happens is the bonded pair of electron, the electron cloud of this particular sigma bond, you know that every single bond contains two electrons. So if you just consider that the electrons are a wave, so definitely you can say that the electron cloud is moving more towards chlorine because the electronegativity of chlorine is more than hydrogen. As a result, we can say that the chlorine atom would become delta negative, just like the induced dipole thing. Delta negative, and this hydrogen would become delta positive. Now that's called a polar molecule. Now if you think about two polar molecules, like let's say I have a HCl molecule and I have another HCl molecule. If we talk about these HCl molecules, so definitely this Cl is delta negative and this hydrogen is delta positive. This is delta positive and this is delta negative. So in between a delta positive and a delta negative atom, there would be a force of attraction. Definitely we are going to call it the dipole-dipole interaction, because this is a dipole and this is another dipole. So this is called a dipole-dipole interaction. Understood? So definitely in HCl we can see that, in NH3 also we can see that, in H2 also we can see that. Now an extra point. This dipole-dipole interaction, the force over here, is dependent on 1 by r to the power 3, not r to the power 6, when the polar molecule is static. But when the polar molecule is rotating, in that case, force is proportional to 1 by r to the power 6. So this is for the rotating polar molecule. So I think you may have an idea what is static polar molecule and rotating polar molecule. If you don't, then we can say that the static polar molecules are definitely the polar molecules, those are solid. And the rotating polar molecules are the polar molecules, those who are liquids of the gases, because they can rotate, they can move, they have the rotational energy, rotational motion, we can say that, right? So that's the thing about the Debye force. Now Debye force is a strong force. This is even stronger than Landon. This is stronger than Landon, right? Now this was all about the Debye force. Now we are going to talk about the Kissom force. Completely misspelling it. And now we are going to talk about the Debye force. Debye force is also stronger than Landon, but weaker than the Kissom force. Okay. So when we talk about the Debye force over here, so this is also called an dipole-induced dipole interaction. This is also known as dipole-induced dipole interaction. So what happens over here? Let's say I have an HCl molecule and I have an argon molecule. Now argon is non-polar, isn't it? But HCl is a polar. We have just learned that. So in HCl, we know that there is a charge separation as delta positive and delta negative, but argon is completely symmetric. Now, because there is a negative charge in it, so the electron cloud of this side of argon, they would feel a repulsion and they would move to the other side of this molecule. And as a result, it would get deformed, it would get polarized, and it would form an induced dipole. Now, are you listening to it for the first time? I don't think so. Because if you just think about it, if I have an iron nail or any sort of iron object in front of it, if I just take a magnet in front of it, okay, so the magnet do have, this is the magnet, so they have the north pole and they have the south pole. So how do they turn this iron into a magnet? Because what they do is as this is north pole, they turn this part south and the other part north, and now there is the attraction power in between north and south. That's the thing we are talking about right now. So they're just aligning, they're just inducing the electron cloud to move into such a direction, where we are getting this induced dipoles over here. Now, after the dipole has been induced, now this polar molecule and this induced dipole would have an attraction power in between them. So this is called our Debye force. So I need a permanent dipole for this molecule and for this type of forces, and I need a non-polar molecule to make this reaction, to make this interaction happen. Now, the force is dependent on, again, 1 by r to the power 6. So these are the three major forces, intermolecular forces, those are there. Apart from that, we have two more forces, which is called hydrogen bonding, and we also have, along with that, we also have the ion dipole interaction. Hydrogen bond and ion dipole interaction would be discussed in the next video, but let me just give you a short idea about what hydrogen bond is. You have learned about this in the chemical bonding chapter, but still I guess you have some doubt about it. So do watch the next video, and I'm just going to give you a small tip. This hydrogen bonding is a special case. It is a special case of Keystone force. Just remember that. Now you learned about Keystone force. Now I'm going to teach about the hydrogen bonding after this. So definitely you'd understand all of it. And what is ion dipole interaction? Another tip about this, ion dipole interaction is the reason why ionic compounds are soluble in water. So how all the ionic compounds are getting solubilized in water? The answer to that question is the ion dipole interaction. So if you feel like these two things are very interesting, and if you feel like you want to watch them, definitely just watch my next video. Thank you for your attention. That would be it for today. Bye everyone.
Stay tuned for more videos like this. Subscribe to the channel.